I've started.
Okay. So in the last class we were designing auctions for more general setting, and our goal is a three-step goal, three conditions that we want to satisfy. First is DSIC property, that means dominant strategy incentive compatible, which basically says is that all the bidders must bid their true valuation. The second property that we want to satisfy is social surplus maximization. The allocation should be such that the goods are divided so that the the total amount of happiness is maximized. That the for single item auction, the good should go to the person who values it the highest. And third is computational efficiency. So to ensure these three conditions, we advocated two-step design process. The step one is you assume dominant strategy incentive compatibility without any justification, and try to design an allocation rule which is computational efficient and which maximizes social surplus. Then the second step is ensuring dominant strategy incentive compatible. And we saw in sponsored search auction setting how we can come up with a allocation rule which is social surplus maximizing and computational efficient. Typically, this step is easy. Now, to ensure dominant strategy incentive compatibility, we studied this tool in a more general framework of single parameter environment. What is single parameter environment? Each bidder has a private valuation Vi, and there is an allocation vector x1 to xn. In some sense, xi is the amount of good that is given to bidder I. Um, and utility of player I is valuation times the amount of good xi that this player I receives minus pi, the amount of payment that player I makes. And we will assume that payments are always non-negative. That means in no circumstances the seller has to pay, and payment is at most the bid value. Then we saw the Myerson's lemma. It is a strong result which says that for a single parameter environment, an allocation rule X is implementable. That means it is possible to come up with a payment rule so that the allocation rule plus the payment rule, the whole thing will be dominant strategy incentive compatible if and only if the allocation rule is monotone. Now, what do you mean by monotone? The allocation function for each player I, you yes, here for each player I, for each player I, you fix the bid values of other players, all other players, and you see the allocation of player I as a function z of the bid of player I, and this function xi in the parameter z should be non-decreasing. In plain English, increasing the bid value should not lead the any bidder to get less amount of stuff. So that is monotonicity, and not only that, the Myerson's lemma says that if the losers pay zero amount, then the payment rule is unique. And moreover, the payment rule can be given as an explicit formula. We have seen for two special cases when the allocation function xi is piecewise constant function, then the payment for player I is given by this function. You look at all the jumps and you multiply the place of jump times the amount of jump, and you extend this same concept to continuous and integrable uh, functions exercise, and there you integrate it over the interval 0 to b, 0 to bi. Okay. Then we applied this Myerson's lemma to sponsor such auction and got this payment. Then I finished yesterday's lecture with two exercise problems. first problem is third price auction. Like the winner is the highest bidder, but he or she pays the third highest bid. Assume that there are at least 3 bidders. Is this DSIC? Has anyone solved this? Okay, these are not difficult, so I'll leave these exercises for you to solve. I think this you can use as hint for class tests, class test questions. The class test questions will be like this because the exam will be open book exam, so you can think of, you can prepare for this kind of questions. Okay, so in today's lecture we will see another sort of setting and design a auction and a desirable auction for this particular setting, which we call knapsack auction. So what is the problem? So to motivate this, suppose so here is the problem, and we will motivate also. Each bidder I has a publicly known size Wi. So think of each bidder as a potential advertiser for a advertising slot of a popular TV show. So in a popular TV show, suppose after 10 minutes there will be a 5 minutes break, and we need to decide which ads will be shown in that 5 minutes. And each bidder is a potential advertiser who want to show their ad. So the size Wi you can think of as the amount of time that it takes for the advertisement of bidder I to show. So that is the publicly known. Then each bidder I has a privately known valuations. Valuation VI. Okay, and the seller has a capacity. The seller is the one who wants to decide which ads will be shown in that 5 minute slot. The seller has a capacity W. Okay, and what are the allocation vectors? So suppose there are n bidders, as usual there are n bidders. And what are the feasible allocations? Allocations. So it is all x1 to xn. Each xi should take value 0 or 1, is 0 1 to the power n, such that the size constraint is made. That means the total amount of total size of the items picked, that means summation xi wi I equal to 1 to n, this should be less than equal to w. So this is the set of all possible allocations. Okay. Okay. Now can someone tell me what is a surplus maximizing allocation? Again recall, we are advocating that two-step design process. In the first step, we will assume without justification that every bidder is explicitly telling their true valuations, and we will ensure the first goal is to design an allocation rule which is surplus maximizing and if computationally efficient. So surplus maximizing allocation. So what is surplus? So for bit profile, say B1 to Bn, B1 to Bn. For bit profile B1 to Bn, the x1 to xn which is a function of B1 to Bn. What is this? This is the argmax summation Bi xi I equal to 1. This is just from the definition. For the allocation x1 to xn, the social surplus is summation Bi xi, and to pick a we want to pick a allocation rule allocation which maximizes this surplus. So we pick a allocation x1 to xn which maximizes summation Bi xi. Okay, so first step is done. We have ensured a surplus maximizing allocation. Then the second step is invoking Meyerson's lemma because it is single parameter environment. Why? Because the private information of each player is encoded by a single real number. So that's why it's a single parameter environment. So let's see consider payment rule. So how does recall how should we compute the payment for ith player? So I will look at the I'll fix the bits of other players and I look at this function xi z b minus I. Can someone tell me how will this function will look like? Feel free to unmute and answer. How will this function xi of z comma b minus I will look like? It's a function of z. Yes. Please unmute and answer.
Sir, so I have a
Yes.
confusion regarding BI. So if we have
Mhm.
assumed that the process is DSIC, then why aren't we using VIs instead of BIs?
Oh, here we can use VI also. Here I can write VI also. That is also fine. Is that okay?
So but VIs are constant, right?
Yeah, so that's why I write BI because when you are defining allocation rule, allocation is a function from bids to allocations. So that's why I write BI here. So here I am defining an allocation rule, and allocation rule by definition is a function from bit profile to allocations. That's why I did not write vi there, but you are right. So at the end, when our mechanism will be DSIC, their bits will be vi, and indeed the allocation rule that will be picked will be the allocation rule x1 to xn, which maximizes summation vi xi.
So we are writing this as the general allocation rule, which
Allocation
is
rule.
a
This is the
function of bits.
allocation rule.
But yeah, this is a general allocation rule, which is a
Correct.
function of bits. But when we apply DSIC, it will become VIs.
Exactly. Exactly.
Okay.
So for defining an auction, we need to define allocation rule and payment rule. For example, when we talk about first price auction, we define allocation rule. Who will be the winner? That rule we define to be as the person who bids the highest will be the winner. The same thing is here. Okay. Yeah, good. Feel free to unmute and ask questions if something is not clear. Now I am defining payment rule. And payment rule again, I am defining means I want to define this. Payment rule is also payment is also a function of B1 to Bn, and it has, so I'm defining, it has n components P1 to Pn. I am defining Pi of Bi B minus I. This I am defining for I in n. So to define this, I need to look at the allocation rule xi. I am invoking Meyerson lemma because it is single parameter environment, and the allocation rule is surplus maximizing, is a monotone allocation rule. So here let me write, check the above allocation rule is monotone. So by Meyerson's lemma, there exists a unique payment rule which makes this entire mechanism dominant strategy incentive compatible. Now I am defining that payment rule. Now can someone help me with this function xi z comma b minus I? How does this function look like? In the range 0 to bi. Please, this is not difficult.
Non-decreasing.
Yes, it is non-decreasing. That's what monotonicity means, but something more specific. Okay, so if you fix the bid values of other players, you see the allocation is maximizing summation bi xi. Now, if you make z equal to 0, then of course it won't be picked because it does not make sense to pick. Now, if you keep increasing z till certain value, there will be a certain point. Let me erase bi here. There will be a certain point. Say, let's write it here. Let's write ci, which is a function of b minus I, the other bits, where beyond which this item I will be picked. So this allocation really looks like it is 0 till a certain value, and once it's crossed that value, this item will be picked. This is one form, isn't it? These xi's are 0, 1 values. If ith bidder bids 0, then it won't be picked because that fix some b minus I. Now, if we keep increasing the bid value of the ith bidder, then there will be at certain point, certain threshold beyond which that item will be picked. Is that fine? And this is 1. This jump is 1. So this payment is by from Meyerson's lemma. This is Ci times 1, which is Ci. So every so this is Ci if Ci is greater than equal to Bi. If player I wins, then it pays Ci and 0 otherwise. Because recall in Meyerson's lemma, we add these jumps only till the its bid value Bi. So every winner pays his or her critical value. Ci. Okay, is this sort of clear? It comes from here. In last class, we have written this formula here. The payment formula is that till Bi you go, and if there are L jumps, you look at the places of jumps and multiply the place of jump with the amount of jump. Now, for in our case, there is only one jump, and it is at the critical bid Ci, and its jump value is 1. So Ci times 1. Question. So does this auction now satisfy all our desirable properties? So what are the desirable properties? Let's recall. First one is DSIC. Second one is social surplus maximization. And third one is computational efficiency. Okay, so does our auction satisfy all these three properties? Yes, no? How many of you think it is yes? Raise your hand. Raise your hand if you think that it satisfies all the three properties. No one? Okay, raise your hand if you think that it does not satisfy all the three properties. I don't know. Everyone is blank. Are you following what I am saying? How many of you studied yesterday's content? These things are not sort of super trivial. Just raise your hand if you have studied. We are not noting the names down. Just truthfully raise your hand if you have studied yesterday's content. Okay. Yes. So please, there are these lecture videos are recorded. Please listen to the lecture videos. Otherwise it will be you won't understand anything. Yeah. Okay. Okay. So I'll let you check that. Of course, by design, social surplus maximization is satisfied because we are defining the allocation rule to be the maximizing allocation which an allocation which maximizes social surplus. That is from the definition. And because this allocation rule is monotone, because from Myerson's lemma it follows that once we implement this payment rule, then it is also DSIC. But this is not computationally efficient. Why? Because this payment rule is not computationally efficient. Let me write here. This is an NP-hard allocation rule. In plain English, we do not know any efficient polynomial time algorithm for how to pick an allocation rule which maximizes this sum. This computational problem, that means given bit values b1, b2 to bn, pick pick an x1, x2 to xn such that which is a valid allocation, that means summation xi wi should be less than equal to capital W, and subject to that constraint it maximizes this summation bi xi. This is a computational problem and we do not know how to solve it efficiently. So this breaks in the third point. Okay, computational interactability. So what do is to make it computationally efficient. Let me write. To achieve computational efficiency, so because the social surplus maximization problem itself is computationally intractable in this case, if we want to achieve computational efficiency, we have to relax the social surplus maximization. We need to be happy with approximate social surplus maximization. To achieve computational efficiency, we modify allocation rule which is computationally efficient and not too bad on maximizing social surplus. That means and approximately maximizes social surplus. Okay. So now it's an sort of an algorithm design problem, and also we need to achieve, don't forget that we have to ensure DSIC, so the allocation rule must be monotone. So to achieve DSIC, so not only it has to be computationally efficient, it also must be monotone to achieve DSIC, so that we can apply Myerson's lemma, because in single parameter environment only monotone allocation rules have corresponding payment rule which makes it dominant strategy incentive compatible. To achieve DSIC, the allocation rule must be monotone. Okay, so let's see. So now we design a greedy algorithm for this problem, and by the way this problem is called knapsack problem. That means you are given n integers, and with respect to the size constraints, these n integers are these bit values b1 to bn, and each item has a size wi, and there is a knapsack of size capital W, and you need to pick items so that the entire weight of the item is less than equal to W, it fits in the bag, and the value is maximized. The value is summation Bixi. This particular problem is knapsack problem, and hence the name of the auction, knapsack auction. Okay, so so here is our new allocation rule. So first, by renaming, let's assume renaming. Let us assume that B1 by W1 is greater than equal to B2 by W2 and so on. So bid per unit weight, per unit size. So we are sorting and renaming the items like this. Now we have so here are the sizes. Here is the first size W1. This is W1. This is W2. See how much can be packed in the size W. Suppose suppose you can pack till K, till WK, but this WK plus 1, the K plus 1, this item you cannot pick. So W falls maybe somewhere here in between. Okay. So you sort. Second is that you pick winners. Winners means that you set the corresponding xi value to be 1, you pick them, you pick winners in this order till you can. That means till you reach the capacity W. Okay. Uh, Now third step, return. Okay. So suppose return either the solution in step 2, that means the items you have picked in this solution in this step, or the highest bidder, whichever is maximum, whichever has more surplus, the highest bidder. Bidder, whichever gives more surplus. Means what? Suppose what is the surplus in the second step? So let me write here. So if you pick the solution in the second step, then the surplus is W, not W1, B1 plus up to Bk, because you are picking item till kth item, so Bk. So either you pick this, you look whether this is more or max of Bi is more. Whichever is more, you output this. Okay. So clearly this is efficiently computable. All the steps can be implemented in polynomial time, and and I let you check that it is also easy to check that the allocation rule is monotone. Indeed, if focus on any particular player I, and if player I is winning, and if we increase that player I's bid, then the player I will continue to win, which is very obvious from here. So you take max from this two. Okay, that is if bidder I wins, he or she continues to win. If he or she increases bid. Okay, now everything is good. We just need to ensure how much we have lost in terms of social surplus maximization. And here is a theorem. We claim that we have lost at most 50%. Again, truthful bidding is guaranteed because the allocation rule is monotone. Hence, the combining the payment rule, the mechanism that we will get there, every player will bid truthfully. That is, this is from Meyerson lemma. So, assuming truthful bids, uh, so so let's call this a greedy allocation. Okay, so greedy allocation achieves at least 50% of maximum social surplus. Okay, so we have lost at most 50% in terms of the quality of the allocation. Okay, so proof. So let opt be the opt is maximum social surplus, and say alg is social surplus of greedy algorithm. Okay, so to show that alg is greater than equal to half opt. Okay, so here is the thing. What is okay? What is opt? You see, because we have sorted the bits in the increasing order of bi by wi, the opt is at most summation b1 to bk. So opt is less than equal to B1 to B, sorry, not BK, BK plus 1. Now, you see that this is at most alg, okay, because alg is maximum of B1 plus up to BK and max BI. So alg is greater than equal to B1 plus dot up to BK, and this BK plus 1, alg is greater than equal to BK plus 1 also. Why? Because alg is greater than equal to max of Bi. So in particular, alg is greater than equal to Bk plus 1. So what we get is alg is greater than equal to opt by 2. Okay, questions? So this is the whole field of algorithmic mechanism design, auction design. For various scenarios, in many real world scenarios, it turns out that designing the uh, surplus maximizing allocation is often a intractable problem and NP hard problem. And then because efficiency is sort of must, then we sort of go to this sort of approximate social surplus maximization, some algorithm which is some other allocation which is monotone. We need monotonicity for DSIC, and it maximizes social surplus approximately. Here it guarantees that at least 50% of social surplus is attained. And in for this particular problem, we can there exist more sophisticated allocation rules which can be computed in polynomial time, and this 50% can be pushed to 99.99% or arbitrarily close to 100%. Okay, so I think because you are, I don't know, most of you are blank, so let me not continue further, and let me in the rest of the time let me spend some time on these exercises. But please study, these are not super trivial things. So let's look at the third price auction. Okay, let me write the answer. It is not DSIC. Can someone say why it is not DSIC? Or why this is not DSIC? So one straightforward way to prove that this is not DSIC is to come up with a number of players and their bids, their valuations, and show that look, in this particular scenario, this particular bidder is better off not bidding his or her true valuations. That will be a direct way, but there is a very straightforward way also from Meyerson's lemma. Can someone try to prove this from Meyerson's lemma? I claim that this follows as a corollary from Meyerson's lemma that the third price auction is not DSIC. Why this is not DSIC? So here is the Meyerson's lemma for you. See and answer. I don't know, so I can't help. So it immediately follows from Meyerson's lemma. You must study, otherwise there is no point giving us lectures. So what does Meyerson's lemma say? It says that in a single parameter environment, monotone allocation rules are the only allocation rules which are implementable, and the payment rule is unique. Now look at third price auction. We have seen the for the allocation rule which gives the item to the highest bidder. For that particular allocation rule, the second price auction is dominant strategy incentive compatible. Bidding true values, bidding their valuations is a dominant strategy, is a best strategy. So any other payment rule will not be DSIC, straight from Meyerson's lemma, because if you fix a payment rule, then the if you fix a allocation rule, the payment rule that makes it dominant strategy incentive compatible is unique. And because the payment rule of making the winner pay the second highest bid makes the allocation rule which allocates the item to the highest bidder dominant strategy incentive compatible. Hence any other payment rule, namely the payment rule which asks the winner to pay the third highest bid, cannot be dominant strategy incentive compatible. Is this clear to everyone? This follows from uniqueness of payment rule. Both second price auction and third price auction, the losers pay zero. If losers pay zero, then payment rule that makes certain allocation rule dominant strategy incentive compatible is unique, and hence the third price auction is not dominant strategy incentive compatible. Please unmute and ask if this is not clear.
So can we also prove it without using Meyerson's lemma?
You can also prove it, but that will be, as I said, it will be more ad hoc. You have to ingenuitively think of some particular example with 3 or more bidders and their valuations and some bid profile, and show that look, in this particular case it is some particular bidder is better off not bidding their true valuation. But that proof is, of course, at least to me, looks more non-trivial. There are lots of things to design. Okay.
Yes,
Okay.
sir.
So let me. Yeah. Is there any question? Okay. So let me leave question number 2. That is just straightforward application of Meyerson's lemma. You just look at the allocation rule, and it is of course monotone, and you just apply Meyerson's lemma and get the auction. You decide the payment rule, and if you derive the payment rule from Meyerson's lemma, because the allocation rule is monotone, it must be DSIC. Okay, so let me stop here. We'll meet again on Monday. But please study. Otherwise, this will be quite non-trivial to you. Okay.